Dhanbad in 2014, and presently he is working as a doctoral scholar at Birla Institute of Technology and Science, Goa campus, under joint supervision of Professor Tarun Kumar Jha, Birla Institute of Technology and Science, and Professor Vijay Kumar Agrawal, Saha Institute of Nuclear Physics, Kolkata. So, as we know, he is actively working on nuclear astrophysics, which involves a close collaboration among the nuclear and astrophysics. Notably, he is working on equation of states of dense matter at high density, high isospin asymmetry, theoretical estimation of Newton star properties, and their applicability on LIGO observations. So in the period of his period of his doctoral degree, he published several papers in ISI journal and many publications in physical review D and C within the recent years. Today, he will deliver a talk on constraining the nuclear matter equation of state from tides in merging Newton star. So I invite the speaker. Let's start the talk. And also requesting everyone to mute the voice. Okay. Sunil, you can start the talk.
Okay. Can you? My slide is visible.
Yes.
Hello. Yes. Okay. Thank you, Mr. for nice introduction. Today I am going to talk about.
साउंड म्यूट कर दो अपना म्यूट करो क्या हो तुम का साउंड चलाएंगे
One of the outline of the talk is the introduction.
तुमको अपना साउंड म्यूट
17 observations, GW 170817s, and our main studies of the correlations, and finally conclude with the remarks. I will start with a very nice sentence by Professor Hansel from his books of Newton Star Physics 1. The Newton stars play a unique role in physics and astrophysics. On the other hand, they contain matter under extreme physical conditions, and their theories are based on risky and far extrapolations of what we consider reliable physical theories of the structure of matter tested in laboratory. On the other hand, their observations offer the unique opportunity to test these theories. So as you can see that Newton stars are basically in extreme physical conditions. Then the NS are very massive and compact astrophysical objects. So observation from these is very important, and you can see the correlations of binary NS system is one of the most promising source of the gravitational waves observations by ground-based detectors. And the GW signals emitted during this NS merger depends on the behavior of Newton star matter at high density. So from these observations, we can constrain the behavior of matter, the theoretical theory at very high densities. And from the history in 1932, that Chadwick first discovered the neutrons as elementary particles. And in 1933, you can see that it's first the neutron star existed of neutrons are proposed by Bade and Zwick. But it is discovered in 1967, Jocelyn Bale and Anthony Hayes discovered the radio pulsars from a pulsar. Later, all is known as the pulsar is as a rotating neutron stars, and most of the largest number of neutron stars are as the type of pulsars. And what are neutron star properties in brief? As a neutron star is a very compact object, and the central densities of the star is 4 to 8 times the saturation density, and the central mass density of the order of, you can say, 10 to the 15 gram per semi-cube, and the radius of the neutron star of the order of 10 to 14 kilometer, and mass of the order of 10 to 30 kg, and asymmetry is very high. Asymmetry is also of the order of 0.7, you can say. So before going to the detail, we can see the neutron star structures. how the structure equations neutron star looks. It's in the spherical assumption case, the pressure and the mass gradient you can see are related to these coupled equations. This equation known as a tube equations, where you can see that where g is the gravitational constant and c is the speed of light, p is pressure, small m is mass of the star, and a is energy density, r is the radial coordinate. And here the basic input of this this is basically what the inward gravitational pressures and the outward the Newton degeneracy pressures. This is the balancing equations. From there we can see that the basic physics input is the equation called the equation of state. What is that? That how the pressure of the matter is related to the energy density with respect to density, and the boundary conditions are that the mass at the center, a radial coordinate 0, center you can say mass is 0, and when the radial coordinate we start integrating from the radial coordinate to the surface, and then usually you will acquire the mass, and the pressure towards the surface comes down to 0. And from there, in the equation of states, as in key that there are two terminology, you can see that they had that soft equation of state and stiff equation of state. With respect to the mass density and with respect to the energy density, if the pressure is stiffer, then you get a very high mass radius, and pressure is soft, you will get a low mass radius. This equation of state is the key input to calculate the structure of the neutron stars. Now, the tidal deformations. What is tidal deformations? During the last stage of the spiral motion of the coalescing neutron stars, the intense gravity of each of them induced a tidal deformation in the companion stars. And so, when the two neutron stars, in a neutron star merger, due to high gravity, the tidally one neutron star will be tidally deformed due to the other neutron star. And decoding these gravitational wave phase evolutions caused by the deformations can allow us to determine the dimensionless one-time deformity parameter that is called the lambda. That is the dimensionless tidal deformity parameter. That is a degree of deformations, you can say. So lambda is basically 2 by 3 into k2 times c square r by gm to the power 5, where r is radius of the neutron star, m is mass of the neutron star, and k2 is called the second Love number. So lambda is, you can see, the proportional to k2 times radius to the power 5, fifth power of the radius. And two basic some few technical things, and how do we calculate this Love number of this. This is also related to a internal structure of the neutron star, because this K2 is calculated. You can see it is proportional to the compactness. Proportional to the compactness. C is the compactness of neutron stars, and is related to differential equations like this. With the from this differential equation r into dy dr, y is a parameter. If you able to calculate y at surface, then one can calculate the Love number K2, where r dy dr into y of r square plus y of r4 r square equals to 0. Now, this equation has to solve together with the TOV equations, because this equation also, you can see that equation of states is enter here also. So this this equation and previously the structure equation, TOV equation, has to solve together to calculate the Love number. If one know the Love number, then one can calculate the tidal deformity for this particular US. Now, what is equation of states? Equation of states, you can expand the equation of state in terms of neutron proton in the order of neutron proton asymmetry. So in a good approximations, equation of state E of rho comma delta, where rho is the total density, neutron density plus proton density, and delta is the asymmetry, rho n minus rho p by rho. You can expand your E of rho comma delta as E of rho comma 0 plus S of rho delta square. Up to delta square is a good approximations. A ring of rho 0 is the equation of state of a symmetric nuclear matter, where asymmetry is 0. And S of rho is nothing but the symmetry energy of the equation of state. So in SNM, again you can expand the symmetric nuclear matter equation in terms of E of rho 0 and K0 by 2 rho minus rho 0 by 3 rho 0 whole square, where rho 0 is saturation density. So you can expand Q0 by 6 rho minus rho 0. This so you can see these all are the nuclear matter parameters K0, Q0. Neutron star equation of state basically depend on the two parts. One is symmetric nuclear part, and one is the symmetry energy part. From the symmetry nuclear symmetry, and there is various parameters from the symmetric part as well as from the symmetry part, that K0, Q0, these are and the L0, the symmetry energy, slope of the symmetry energy, and the curvature of the symmetry energy. So, so there is a very nice study by N. Alam and his collaborator in 2016 in PRC 94052801. You can see where you can see that the neutron star's radius, basically they have shown the neutron star radius is how correlated with respect to different masses of the neutron star, and they have seen that the individual parameters such like that the K0, which is the incompressibility from the symmetric, which is a parameter of the symmetric nuclear matter, and the L0, which is a slope of the symmetry energy, which is the individual parameters are not that much good correlated. If you are taking the sum of these two, the combination of those two, that K0 plus alpha L0 and M0 plus beta L0, these combinations are very strongly correlated with respect to radius. But this alpha and beta, this multiplier factor here estimated such a way that for which gives the maximum correlations. So for which alpha you can get the maximum correlations. And this is that there is in the GW17017 event that binary neutron star in a binary neutron star merger, they have given the primary mass. There are two neutron star masses. Primary mass in the range of 1.36 to 1.6, and the secondary component of the mass component was 1.17 to 1.36, and they have determined a chip mass. Chip mass is a combination of these two mass that very precisely measure 1.188 plus minus within the error bar, and the combined tidal deformity, or you can the effective tidal deformity, is less than 800 for the low spin pairs. They have with the same confidence limit, they have estimated for the low spin pair as well as for the high spin pairs. In this PRL 199 it is reported. So in our all equation of states, we have considered equation of state. We can we have drawn here in this figure a phase diagram between the two one for two stars tidal deformations. One is lambda 1 for star 1 and lambda 2 in this binary, and this all the curves are drawn such a way that keeping the chip mass fixed. The chip mass is nothing but m1 m2 to the power 3 by 5 into m1 plus m2 to the power minus 1 by 5. If one mass is kept fixed, and at that mass one can draw the lambda 1, and the other mass will be fixed automatically by keeping the chip mass fixed, and the lambda 2 also vary. As we seen earlier in the table, the m1 also has a range and m2 also has a range. So lambda 1, lambda 2 also will follow this range for a particular ABUSS. And they have given a confidence band for 50% and 90% from GW17 events. And one can see here the few stiff USS are out of this bound, such as the NL3, TM1, and SKI5, and the NL3 more or less all the that different combination of NL3, NL3X. You can see that NL3 omega rho, sigma rho, this thing. Here we can say that for the case of NL3X, the value of M0 is larger than 3400, and L0 is 55 to 70, except for NL3 original model. So another case for the TM1X, one can see the M0 is less, little bit compared to the NL3 family, 3100, but L is here high, 110. So either the M0 or L0, either the stiffness comes from symmetric meter part, either the stiffness comes from the asymmetric part. No, the steep US are disfavored for this event, which is confirmed by this event. And now we will study the Pearson correlation. What is Pearson correlation? Well, that for the just completely, I want to say that if from a data set xi yi, it is nothing but the sum over xi yi minus a number of data into x average y average by a number of data minus 1 into standard deviation of x and the standard deviation. This is called the Pearson correlation, standard thing. And we'll study the we studied the Pearson correlation coefficient with respect to for different nuclear matter parameters individually as well as some linear combinations. For the left panel, you can see for the tidal deformation lambda, and for the neutron star radius r, and the correlation for the lab number K2 also. For different mass range, in the top panel you can see for mass 1.2 m solar, then 1.4 m solar, 1.6 m solar. In all cases we have found that none of the individual parameters, nuclear matter parameters, are strongly correlated with neither a lambda nor radius or lab number. But linear combinations, that K0 plus alpha L0, M0 plus beta L0 and M0 plus zeta K0, these three linear combinations shows great or very strong correlations in the mass range 1.4 for 1.4 m solar mass. So this is also, we have seen earlier also that that equation of neutron star properties should depends on the both part of the US. So linear combinations of these giving in the very high correlations. And from there what we can do now, we now from this linear combination we will get one linear regression relations, and there we can constrain the if we have you know the constraint lambda, then we can able to constrain the M0 individual parameters also from their relation. But for that we have to first deduce the tidal deformation for single stars, because at the LIGO can give us very precisely that effective tidal deformation of the both the stars. So now what we have done that we have one correlation studies, one can study that the effective tidal deformations is the equation we can see here, that it is nothing but the equations like this: 16 by 13 into 12q plus 1 lambda 1 plus 12 plus q to the power 4 lambda 2 plus 1 plus q to the power 5 whole to the power 5, where q is nothing but m2 by m1. So that we have studied the correlation lambda tilde and lambda effective tidal deformations is almost 0.999 correlated with the lambda at 1.4. We keep the one mass fixed 1.4, so other mass will be accordingly decided according to the chip mass. So there we have found this lambda 1.4 is 0.859 times the effective tidal deformations. So if one know if one gives the bounds on effective tidal deformation, we can directly deduce the bounds on the for the individual one star at 1 point solar mass, canonical mass. But another work by Latimer and Somi, et al. And Latimer in PRL 121, they have assumed that that the radius in this range of the neutron star range, mass range 1.17 to 1.6 is almost same, R2 by R1, means, and it's two for the two component R1 R2, they have taken the same USS for, and they assume that the radius is almost same. By assuming that, they have deduced that lambda 2 can be expressed in terms of lambda 1 by q to the power 6. That q is m1 m2 by m1, the mass ratio to the power 6. By assuming this, they have also deduced the effective tidal deformation to a single dimension like that. And if you put here q for 1.4 m solar mass, if you put the q is equal to 0.95, and then one will get 0.856 lambda tilde. Although our work is submitted earlier to the journal, but both the work has been done independently. But this also in our earlier version also I will see later that how this also valid this one tidal deformation of one star and with other stars q to the power 6, how this is valid we see the net after few slides. And from there we have constrained by taking the very good well accepted empirical range of L0. If you take that L0 is 40 to 62, this range is provided by Latimer. One Latimer paper is Latimer in 2013 in Astrophysical Journal, and 30 to 86, that range is also very well accepted. That is by Otel. It is in PRC 89 2017. Now this deduced lambda deduced tidal deformation for canonical neutron stars 344 to 687, we have constrained the M0 parameter. So from 2 to 542, 3631, and Ksim is like that, minus 1132, minus 52. And if you take the L0 range like this, 340, 30 to 86, then you can go on M0 will be your 1926236768 and Ksim 0 will be 14016. So although you can see that this M0 is also still now when these parameters, curvature of the symmetry, energy, M0, these are not still not now very tightly bound, because as currently that which the bound we have on the tidal deformation, from this only this much one can bound the parameters. Another interesting thing we have studied that if you for all sets of model, what we have done, we have taken the radius versus the lambda. For all uses, we have taken the radius for 1.4 m solar and the lambda also for 1.4 m solar, and this is very nicely one can see is correlation coefficient almost 0.9. Now it's very strongly correlated. We have to have got that this lambda tidal deformity parameter for 1.4 is related to r to the power radius to the power 6.13 that we got earlier. First we got the 6.13. and the coefficient is 9.11 10 to the minus 5. And we have checked and verified for different other mass range also. For 1.17 the coefficient is of the order of 5.84. For 1.6 coefficient is 6.58. And from the because one can see that as we seen earlier that the lambda is actually proportional to radius to the power 5. The extra power of one radius, that 6, here it is we are getting radius to the power 6. The extra 1 power of radius is coming nowhere from the log number K2. As you can see in the top panel that we have plotted the K2 1.4 versus R 1.4 for all taking account of all RMF and SHM models, and we have found the correlation coefficient is almost 0.8 also. So this K2 also one proportional to radius, this log number. So the one extra coefficient of radius is coming from this log number K2 itself. So there, by implying the bounds of the lambda from 1.4, we have constant the radius is 11.82 to 13.72 kilometer. We got the radius of the neutron star, and there you can see that this one can say that the precise measurements of this tidal deformity will provide an alternative and accurate estimates of M0, K0 and R1.4 currently which bound we have. So another work we have communicated in the which is an archive, where we have done the we have tried to constrain the lambda one, tried to constrain the tidal deformity parameter from the finite nuclear data. From the finite nuclear laboratory based experiments. So whatever available with us, the binding energy, charge radii, giant resonances, from there we have got that this lambda we got is almost 1.4. This comes out to be of the order of 267 plus minus 144, and the radius are also very strong, shortened out to a very narrow range, 11.6 plus minus 1.2, 1.0 kilometers. I think by having my talk got finished earlier, so if anyone has any questions, and anyone can ask. Hello. I want to thank you, my all of collaborators.
Okay, thank you, Tuhin. So now the sessions for the questions and
Okay,
discussion.
Tuhin.
Hello. Yeah.
Tuhin.
Yeah.
Okay. Okay. So one of your slide you have shown that the correlation between. Can you hear me?
Yes. Now I can hear you. Yeah. Tell me.
Okay. So one of your slide you have shown that the correlation between the tidal deformability of 1.4 solar mass and the radius.
Ha.
You have in
Yes.
that
Yes.
graph you have plotted for the not this one, another one.
This one.
This one. So you have
Yes. Yes.
plotted both these SCORM and RMA parameter sets.
Yes. 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 Yes.
But this shows that they are actually model independent. If you take RMA for SHA parameters, they are giving the same things.
Yeah. It is always model independent.
No. Actually, if you in the few days back, I have seen one paper by Ban and Lee. I forget the name.
Normally.
So
Banli.
he clearly state that there is two different things that the correlation are very different in both SHF and RMF, and they have taken lots of parameter sets, and also the power is very different, not very same. Like one is around 5 and another is around 7, something like that, if I don't remember properly, but they're very different from each other.
Yeah, actually, thing is that there is a small trick is here. What we have also found, if we take the RMF separately and SHF separately, the power will be
different.
Yeah, power is different. But thing is that in this power, the power will be different. But another thing is that this coefficient, one coefficient is there with the suppose I got is 9.11 in 10 to the minus 5. This
coefficient range is very different also.
Yeah, but thing is that you can adjust this power little bit, one or two by one can by this power fraction will be can get adjusted by this coefficient also little bit.
But that's why I am asking that. My question is that on the basis of these things you told that the tidal the log number is related with 1 over is proportional to the r, because you are getting around 6 and generally it will 5 and then into another 1 power.
Yes.
But how can we conclude these things? Because this power is not very fixed. You can do up to even if you if you take some subset of SCORM parameter sets, you will get around 7.
You will take some scam. There are some people reported 7 also. Yes.
Yes, even if we are also calculating something like we are getting something like around 7. So then the power will be 2. So my question is that it is very perfect to say that this we can, from this calculation we can conclude anything about the correlation between the radius and the log number.
Because correlation between radius and log number is a good question, but here also we have
Yes, sir.
Subra,
Yes.
so recently Katyagi did a calculation related to the correlation between nuclear matter properties with the tidal deformability. So he has taken the Bayesian analysis approach, and he has also found the same thing as we have done.
No.
To the power c.
No.
My
question is that Bharat, my question is that this calculation, that finding the correlation between the tidal deformability of 1.4 and the radius of 1.4, And actually this is not very strict calculations, because if you fix the coefficient in different range, you are getting the power in different range. In the, if you are fixing the power in different range, you are getting also coefficient in different range. So you can play with that two things and you can get many things from that.
Subrat,
As
if you like, you can show the work what we did for the scorm parameter, so you can
no,
see.
actually I cannot do, because I am talking in that mobile phone, so it's very
Okay.
difficult. Uh, okay, we will
Acha.
discuss to him. We will discuss more about these things personally.
That is one.
Uh, another things is that
Another.
it's not
Yeah.
touching. So why we calculate the only the K2, not K for something like that? Is there any physical significance of K2?
Because significance of K2, because
Because I am
we are.
getting some lots of noise. Okay, okay.
Yeah, can you hear me now?
Yes, yes,
Yes.
I can hear you now.
So this K2, the second lab number is directly related to your tidal deformability lambda.
Okay.
If you do in the derivation the maybe the higher order term, the what is the fourth order lab number or the other lab number is a very in a very good approximation that one can see the tidal deformation is related to 2 by this thing, say that yes, 2 by third K2 into
Okay, okay.
so that is the thing. And another thing is if you just initially one can solve there, one can just see the K2 is just a number, but K2 is not just a number, it also depends on the internal structure of the nuclear star. So for different model you get different lab number. That's why this correlation of K2 is very important. How the K2 is depend on various nucleometer parameters in the model independent way. Hello.
Okay, okay,
Yeah.
okay.
Hello.
Yes.
So I think I mean people determine K2 because that is the quantity you need to calculate for quadruple deformation. If you take higher deformation, then you need to go to higher moments.
Okay,
So
okay.
as we are interested mostly to for
Okay.
quadruple deformation, that's why we go for A is equal to
But the
2.
tidal deformability comes from the this quadruple deformation.
Quadruple deformation.
But there might be higher moments, but
So
right now
lowest
people
order,
are neglecting higher moments.
this is the lowest order.
Yeah, that is the most dominant and lowest order. Yeah.
Dominant and the lowest order. And Tuhin, you have
Yes.
shown one in your one slide. You have shown that there is a correlation between one tidal deformability of 1.4 and the effective tidal deformability.
That is a basically tidal deformity. What's a tidal deformity? One should expect this is a trivial case that correlation should be one only, because the other side also tidal deformity, and this side effective tidal deformity also tidal deformity. Means, but the thing is that this way we extracted. If you take all the models from all the models, if you just calculate the effective and by fixing one mass 1.4, so from there we got that this for individual one star lambda 1.4 is related to the effective just by the factor of 0.859. But if you take the approximation on the other side that lambda 2 is actually lambda is proportional to the sixth power, then explain the one lambda second it's lambda 2 in terms of lambda 1 by q to the power minus 6, and if we just substitute it to the effective tidal deformation, there also one can get that the individual tidal deformation is related to the effective like this way. So here also this approximation, if you derive it analytically, the approximation goes that it is a lambda is actually radius to the power 6 instead of 5 if you neglect the lab number. Hello. What is your question? Hello? Subhat?
Subrat can hear.
Hello, Subhat?
Okay. I think he has some problem in the network. So maybe someone can have other discussions if you have.
Hello.
Yeah, I can hear. Yeah.
So I have a few questions.
Yeah.
So so I have seen. I mean, you guys are taking this combination of M0 plus K0 or K0 sim or L0. So
Yes.
why you choose? I mean, this combination. I mean, this why there is 12 in front of K0. So I mean, how do you choose this combination? M0 is equal to 12, K0 plus Q0. So
Yes. So what is the question? How you choose these combinations?
yeah, because there is a 12 in front of K0, right? So how do you get this number 12? Yeah, I don't get this.
This one.
Yeah.
Yeah. As actually the linear combination, you can see that
Oh, sorry, I lost my connection. Okay.
one parameter is
Come on.
Hello, cannot hear.
Hello. Hello.
Yeah, now it is right. Okay.
Tuhin, can you hear me? Hello.
I don't think he can. Tuhin had some problem maybe, so we'll wait for a little time. But he's online, but maybe the network problem. That's why he do not hear properly.
Okay, so I am leaving. I have some questions, but I will post them in the group maybe later on.
Okay.
Mrityunjay?
Yes, sir.
Acha, who is the one asking question about 12 factor? Can I understand the question properly?
Actually,
Yeah, here is Rana. So I am asking.
Yes, tell me, Rana.
Yeah, so there is some combination you are. I mean, I've seen in your some papers. So how do you choose this combination? I mean,
No. First of all, see, there are two things actually. I mean, are you talking about the combination of M and L, or you're talking about some factor 12?
so I am mostly concerned about M0. So I have two questions. So is M0 directly observable, and how do you choose this combination of K0 and Q0 to get M0?
I tell you, see, if you look at the definition, first of all, the M0 we have chosen because recently it has been shown that normally we think of that isoscalar giant monopole resonance is directly correlated with the incompressibility coefficient K0.
Right.
But it has been shown recently in couple of the PRL paper that is not the K0, it is better correlated with the M0. Okay, now what is M0? M0 is a derivative of K0. Okay, so if you really look into the definition of M0 and if you expand the definition, then it can be expressed in terms of 12 K0 plus Q0.
You said M0 is the derivative of what?
K.
Oh.
K. So if you write the definition, if you look into definition of M0 and if you just, expand it, because you can visualize yourself, since M0 is the density derivative of K0. So you get one term which is K0 and one term which is the cube derivative of the energy density function that gives rise to Q0.
Okay.
So at rho 0, if you look at it, it is nothing but the 12 K0 plus Q0. So the 12 factor comes from there.
Okay.
As far as the choice of M0 and L0 is concerned, as I told you that M0 seems to show the better correlation than K0. Okay, so that is why we took M0 because see.
Yeah, that I got. Yeah.
Because our idea was that if all the properties of star should be correlated to some isoscalar properties and some isobacterial properties, because since we decompose the entire US in two parts, SNM and the energy, so the properties of star combination of isobacterial properties. And since K0, M0, these are basically the leading order contribution to the US for the SNM.
Yeah.
Whereas L0 is a leading order contribution to the symmetry energy. So we looked at this kind of combination.
Okay, thank you.
Now
hello,
Tuhin
sir.
back.
Hello, sir. My one question to Vijay sir.
Bolo.
That means the m0 is the first derivative of the compressibility with density.
Yes.
Means it is the third derivative of if you expand in the terms of energy density, it will be third.
It will be actually, see, the thing is the following. You have to really start with you have to write normally when we say the compressibility is 9 rho square times double derivative.
Double derivative. Okay. That's why I'm
So you have to keep in the mind one thing, that is true only at rho 0.
Okay,
because
that's not true for the other
other
below
density.
or density.
No, because the thing is the following. You have to write down the definition of compressibility in terms of pressure.
Okay. Yes.
Okay. Now you expand your definition, then you will encounter one term which is the dd rho of energy per particle at a given density.
Yes.
Since we are talking about the quantity at the saturation density, that term goes to 0.
Okay. Yes.
Okay. So this 9 rho square times double derivative, this is strictly the definition at rho 0.
Okay.
Okay. In principle, what you should have is 9 rho square times double derivative plus some term which involves single derivative.
Okay. So that is 0. Okay.
That is a two definition. Now you take a derivative of this definition. Okay. So what will happen? Wherever you have double derivative, that will become triple derivative. That will contribute to Q0.
Q0 and another thing
Yes,
compressibility.
That become exactly.
Okay, I understand now.
So that is how the combination of. So you have to remember very carefully to start with the right definition.
That's why I'm thinking that too, because if you saying that is only the one derivative higher of the compressibility, then one became third derivative, another became second derivative. So that was my confusion.
Exactly. So you have to keep in the mind in the real sense, the compressibility is double derivative plus.
The definition of the compressibility is something like that.
You have to take the definition at any density. If you take at rho 0, then you will go wrong actually.
That's why I'm saying that it will go wrong.
First, I have one more question. So, in all those, in the table, the lower bound for lambda 1.4 is always 344. So, how did you get this number?
This lower bound we have taken by that one bound by that 400. That's that I will tell you. That we have taken that UV optical inferred counterpart of GW 17017 with kilonova models and compared in one astrophysical paper. They have given the lower bound is 400 by analyzing that UV optical inferred counterpart of GW 17.
But that is for lambda tilde, right?
That is for lambda tilde 400. So if we extract this, if you use this relation that 0.85, then it will come to.
Okay, I got it. Yeah.
Tuhin.
Yes.
So whenever you are choosing that RMF and SHF parameter, different set of parameters, so have you underline any type of symmetry, something like that? You are choosing like on the basis of the symmetry energy value or compressibility value or something like that? Only you have taken these parameter set which have compressibility in that range.
No. My compressibility and these are in a this wide range. Means already one thing we just consider all the neutron star mass should are above 2 m. So means within the accepted bound from 1.9 above 1.97. The incompressibility wise it is not filtered like this way. And I will just hold on. I can tell you that incompressibility how ranging from where to where. For all the models. Yes. Just 1 minute. Yes. For all the incompressibility is range 240, 270 also there, 280 also there, 230 also there.
Means
so we have not done any filter in the incompressibility level.
So you are only filtering on the higher masses.
Yes, mass. Only we have taken all those kind of models or the maximum mass is satisfied.
So that's actually one thing is that if you are taking the mass as a filters, so it is a very natural that the compressibility will be in a one line. Basically, they are correlated. Tidal deformability.
No, Subrat, we have put only the lower bound. See, we have not taken all of them has to mass 2. We have taken all of them has to be 1.97.
1.9.
Okay. So you are even taking the mass like 3?
For example, NL3, 2.7.
NL3, 2.7, yeah.
Okay. For the storm parameters, what is the maximum mass?
Maximum mass is around 2.
Okay. Okay.
No, there are some equation of state in SkyM also. They generate 2.25 or 2.3.
Yes, I think we have it. I think some
Yes,
VSK.
some VSK
we have SK 2.21 and SKI 5